also thanks to the organizers for this very nice conference and the scientific committee for giving me this opportunity to give a talk. So we'll formalize the classical notion of deconvolution and apply it to obtain growth and deconstruction for monoidal double categories. And this is sort of a companion to a talk that I gave at Ithaca Fest last October. Then I focused on monoidal two categories. Here it is monoidal double categories. So first some motivation that is given by decorated clothespans. They are used in applied category theory to model systems, any systems really, with in and outputs. I want to look at this definition by Peterson. So this starts with a Lex double functor between clothespans in a category C with finite colimits into a spans of categories. So given that Lex double functor, the double category of F decorated clothespans is a double growth deconstruction of F in the sense of Crutwell and Lambert, Pronk and Zill. So this double category should really be a monoidal double category because the monoidal product of decorated clothespans should model running these systems in parallel. So the first part of the aim of this talk is to show that the growth deconstruction is a Lex monoidal double category whenever F is a Lex monoidal double functor. So then that is sort of monoidal double growth and deconstruction. We want to, the second part of the aim is to show that actually is a growth and decorresponds for monoidal double categories. So that's where we want to end up at the bottom. We will take a formal approach to this that will simplify things greatly, and our formal setting will be augmented virtual double categories. In those we will consider formal Yoneda embeddings. We will regard these growth and decorrespondences as formal Yoneda embeddings. Then the main theorem will show us how to lift algebraic Yoneda embeddings. So using that we can lift growth and decorrespondence for double categories to one for monoidal double categories. So we start with these augmented virtual double categories. They have objects and vertical morphisms like F and G here, and horizontal morphisms like on the bottom here with a bar on their arrow. Then there's two types of cells, unary cells, where the horizontal target is a single horizontal morphism. Horizontal source is a path of horizontal morphism. So that includes the empty path, so then you get a triangular cell like this. That is what you call a virtual double category. That's what you use when you cannot compose your horizontal morphisms. If you also don't have horizontal units for your objects, then you also want to use these nullary cells where the horizontal target is empty. So then you get an augmented virtual double category. That includes cells where both the horizontal source and target is empty, so then you get what I call vertical cells. So there is a vertical composition both of morphisms and of cells and identity morphisms and cells. One remark here is that these vertical cells always form a two category in any augmented virtual double category. Two examples here then, simple examples we'll start with. OpFib has large categories as objects, functors as vertical morphisms. Horizontal morphisms are op fibrations with A op and B as the base, right? A is the source, B is the target, whose fibers are small discrete, so they are small sets. Then we also have the monoidal variant, large Lex monoidal category. So Lex monoidal means it's unbiased, right? We have a monoidal product for every arity. Vertical morphisms, functors that preserve the monoidal structure lexically. Horizontal morphisms, well, they will be between any two Lex monoidal categories, but let's, for simplicity, I'll only tell you what the ones are with the terminal monoidal category as source. These are Op fibrations as before, but now the total category has a Lex monoidal structure, and the op fibration preserves the monoidal structure strictly. Right, so that is what augmented virtual double categories are. We want to move to this formal notion of UNADA embedding, right? So for that we need to use nullary restrictions. Nullary restriction of object C along two vertical morphisms into it is a horizontal morphism between their sources that I denote by C of F and G that's defined by a universal Cartesian cell. It's not too important what this universality is. If one of the two vertical morphisms is the identity, then we get what is called the companion and the conjoint of the vertical morphism. Companion is the morphism on the left, conjoint is it on the right. So in OpFib, these restrictions are given by comma categories. So C of F and G is the comma category. But we want this to have small fibers, right? So that only exists if these homesets are small. Companion and conjoint are given similarly. How about non-OpFib? Well, this forgetful functor creates nullary restrictions, but only if the functor on the left is strong monoidal, right? So it needs to preserve monoidal structure up to isomorphism. Okay, using that we can formalize UNADA embedding. So UNADA morphism is a morphism Y from A to A hat, such that all nullary restrictions of A hat along Y on the left and any morphism G on the right into A hat exist. And choosing such nullary restrictions for every G induces functor of Lex slice categories. So the source of that functor is the Lex slice category of vertical morphisms into A hat, and the target of it is the Lex slice category of horizontal morphisms out of A. And we require that induced functor is an equivalence. That's when we have a UNADA morphism. So, first example here, the usual UNADA embedding for the terminal category, pre-sheaf object here is small sets, is a UNADA morphism in OpFib. You can see that because these nullary restrictions, in that case, they are, it's easy to see that those are exactly the Grothendieck constructions of a functor into small sets. And that induced functor being an equivalence is exactly the Grothendieck correspondence for discrete op fibrations. On the previous slide, we saw that nullary restrictions lived along this forgetful functor. So, do UNADA morphisms lift as well? The answer is yes. And the idea is that we see mono-OpFib as the augmented virtual double category of Lex algebras over the free strict monoidal category monad. Well, that I denote by underscore. One remark here, so if you know what the UNADA structure in two categories, that also gives you functors of slice categories, but they go in the opposite direction. And the horizontal morphisms there, they are instead admissible morphisms, if you know of the definition. That will be a fully faithful functor in the opposite direction, but it won't be an equivalence in general. So, in particular, I don't think what we're doing here that you can do it with UNADA structures. Well, that's a big difference. Right, so back to lifting that UNADA morphism along that vertical, along that forgetful functor, right? So that's what this main result will be doing. It's about a monad T on an augmented virtual double category, and its Lex T algebras form an augmented virtual double category that we denote by Lex T algebra. So, given a Lex T algebra A with structure map alpha, right? So alpha goes from TA to A, and the UNADA morphism for A, we assume that this horizontal composite of the companion of the structure map and the T image of the conjoint of the structure map and the T image of the companion of the UNADA morphism exists. I won't go into detail here, but that's a horizontal morphism like this, from A into TA hat. And by that equivalence induced by Y, that corresponds to a vertical morphism V from TA hat into A hat, such that the composite is the null jurisdiction of A hat along Y and V. So under some conditions, V forms a Lex-T algebra structure on the pre-sheaf object. With respect to that structure, Y becomes a pseudomorphism, and the effect it becomes a eunatomorphism in Lex-T algebra. So in particular, we obtain an equivalence between slice categories, again, Lex-T morphisms into A hat and horizontal T morphisms out of A. So our first example, that's what we wanted to do, lift the Uneda embedding for the terminal category along the forgetful functor. It has a unique monoidal structure, the terminal category. The induced structure on small sets, right, that V that we get is simply the Cartesian structure. And that Grothendieck correspondence that we get is between Lex monoidal functors into small sets and monoidal discrete of fibrations. So this is sort of like a monoidal Grothendieck correspondence. It's a variation on the result of Müller and Fasila-Kopoulou. They consider general fibrations, so it's a restriction. So here's one more example. I didn't talk about prof yet, but there's also an augmented virtual double category of prof functors between large categories whose images should be small sets. So if you have a Lex monoidal category, you can consider its Uneda embedding, that's a formal Uneda morphism in prof. You can apply the theorem and you get induced structure on the pre-sheaf category. It's exactly the usual day convolution on the pre-sheaf category. Right? So I sort of think of this induced structure on the pre-sheaf objects as a formal notion of day convolution. One remark here is that if A is large, then pre-sheaves on A will not be locally small, so that means it won't have a horizontal unit prof functor. So in this case, we really need augmented virtual double categories for this to work. Right, so now we want to do everything again, but with double categories. Right, so the starting point is this Grothendieck correspondence for double categories. I mean pseudo-double categories of Pratwell and his co-authors. So the base is a double category. The classifying object in this case is the double 2 category of spans of categories. A double 2 category is a category internal to the 2 category of 2 categories, 2 functors and 2 natural transformations. So the correspondence is between Lex double 2 functors into span cat and the double split of fibrations. Those Lex double 2 functors into span cat, they are a bit like the usual Lex double functors. So we have an ordinary functor G0 between the categories of objects and an ordinary functor G1 between the categories of horizontal morphisms. And these preserve horizontal composition and horizontal units Lexly, so we have a Lexiter and a uniter, but they can be pseudo-natural, right? So that's where we start using this, that span cat is a double 2 category. And also there's invertible globular associativity and unit modifications for this Lexiter and uniter. So then again we use that span cat has this 3-dimensional structure. So these Lex double 2 functors, they correspond to double split of fibrations. They are strict double functors between 2 pseudo double categories, such that the functors J0 and J1 are split up fibrations, and such that this source and target functors here, right, who send the horizontal morphism to its source and to its target, they preserve the cleavages strictly, and the horizontal composition and the horizontal unit preserve Cartesian morphisms, these factors. So that's the Grothendieck correspondence to 4 double categories. We want to apply our main theorem to this, right? So we want to see this as, regard this as some formal unit embedding in some augmented virtual double category. Well, that virtual double category exists. Objects are large double two categories. So the vertical morphisms and the horizontal morphisms are exactly as they were on the previous slide. Lex double two functors and double split up fibrations. But there will be more general horizontal morphisms where, source and target are both double two categories, but let me not go into that. And then the vertical cells between the Lex double two functors, they are Lex double two natural transformations. The nullary cells of this form, where this source here is the terminal double category, they are Lex double Lex natural transformations from this constant double functor that picks out that object D into this composite G after J. So J is that top vibration, satisfying some equivariant section. And these nullary cells, we need to define this double Uneda embedding for the double terminal double category as a Uneda morphism in this augmented virtual double category. So one remark here, remember that at the beginning I said vertical cells of an augmented virtual double category always form a two category. That means that we cannot have these Lex double Lex natural transformations as vertical cells, because Lex natural transformations don't form a two category. So this is again another reason why I don't think you can do this with Uneda structures, because then you need a two category. Right, so now that we see it as a formal Uneda morphism, now we can apply the main theorem. We get the Grothendieck correspondence for a Lex monoidal double categories. So those are double categories with internal Lex monoidal structures. So with an associator and a unitor, monoidal associator and monoidal unitor, that those functors combine into a Lex double functor, and those transformations combine into double transformations. So the correspondence is between Lex monoidal Lex double functors, double two functors, into a stank-cat with the Cartesian structure, and on one hand, Lex monoidal double split up fibrations on the other hand. So what is a Lex monoidal Lex double two functor? It's Lex double two functor is as before, and now we have natural transformations that make the G0 and the G1 into Lex monoidal functors, right? And then again we use a three-dimensional structure. We have globular modifications that make the G those natural transformation into a Lex double two natural transformation. That's what we have on one hand. On the other hand, we have double split up fibrations as before. Now the total double category is equipped with a Lex monoidal structure, such that both J0 and J1 are strict monoidal with respect to those structures. The tensor products for J preserve cleavages, and this is somewhat strict. The components of the monoidal associator and unitor in J, they should be the chosen up Cartesian lifts of the corresponding components for B. So that's what you get. So one remark, if B is a monoidal double category, so that means that this tensor product is a pseudo-double category, a pseudo-double functor, and associator and unitor are invertible. Then J is so as well, precisely if these modifications are invertible. bit quicker than usual. He will be happy.
So let's thank our speaker.
Let me say. Let me quickly say two takeaways. So we saw that formal category theory for double split fibrations and monoidal double split fibrations is possible. So that also means any formal proof of a result in terms of these augmented virtual double categories should immediately apply to monoidal double categories or double categories. And we also saw that yes, if we formalize the convolution, then that sort of gives us monoidal Brofody correspondences. So we can sort of unify these two important concepts. Okay, thanks a lot for your attention.
Question, Eugenia.
Thanks for your talk. I just have a question about augmented virtual double categories. Can you express that generalization in the context of T multi-categories?
No, you cannot. No, you can see them as certain monoids in skew monoidal categories, but not in as a generalized double multi-category.
Over here.
Thank you for a nice talk. Can you go back to your main theorem, please? So you have that pointwise quick composites. Do you know conditions under which that exists? You assume that a pointwise weak composites formula exists, right?
Yes. So I mean, what this formalizes is, I guess, for the composite to exist, you need so the structure that maps into TA, so you need that to be sort of small, right? Because the composite will be given by like a covalent formula. It will be given by a covalent formula. And yes, pointwise really means that it is given all the points by a covalent formula. So that's what it formalizes.
Anybody else? Yeah.
Is your theorem on the monoidal double Grothendieck construction an application of this theorem, or you prove it more by hand?
Say again?
So, if you go to the last slide before, thank you.
Yes, that is comes from the main result. Yes.
Yeah, is this an application of the other theorem of lifting to algebra, or you prove this more by hand looking at?
No, this is an application of this. That's your question, right?
Yes, that's my question.
Oh. So the answer is yes.
Anybody else? Let's thank our speaker again.